So again, here's quiz 4.4b, and number 2 we're going to deal with, and this is kind of a variation on the river problem where we have a rectangle and one side's on the river and the other three sides we want to fence. Well, this is going to be, like I said, a little bit different. You have 1,200 feet of fencing to enclose a rectangular plot of farmland and subdivide it into 3 smaller rectangular regions by placing 2 fences parallel to one of the sides. What's the largest area you can enclose? So I gave you a little sketch here so you can see about what it's going to look like. And these are the 2 sides that are parallel to one side. And we want to find the largest area we can enclose. So let's take a look at this. And what we've got here now is a situation. Now, again, we can call the length x, and the width of this rectangle y, and the area we're going to enclose, area will equal just x times y. Now you could say, well, what about the fences? Well, they're just real skinny, so they're not going to really make any difference as far as the area is concerned. So this is all the area we can enclose because the fence is trivial. So this is what we want to maximize. We want to find the largest area we can enclose. Now, again, we have 2 unknowns, so we're going to use this constraint. That's the other information, and that's at the perimeter. So this is our constraint. And that is that the perimeter equals, well, it's not the perimeter, excuse me. It's the amount of fencing we have, but it's kind of, in a way, the perimeter equals 1,200 feet. And maybe I should just say the fence we've got. The fencing equals 1,200 feet rather than the perimeter because we have 1,200 feet of fencing. It's kind of like a perimeter, but we'll just say F for fencing. And then how much fencing do we have? Well, we're going to use X over here, Y over here, but we're also going to use Y there, Y there, Y there, and another X there. So the fencing we're going to use will be X, X, Y, 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 Y. So my 1,200 feet over here will have to equal 2x plus 4y. That's my constraint. That's my fencing. Okay? And you can kind of think of it like perimeter because it's going around there and it's kind of more complex perimeter or whatever. Okay? Now we can divide everything by 2 because 2 goes into each of these terms. So that's the same thing as saying 600 equals 1x plus 2y. We want to eliminate one of our variables, so what I can do is I don't want to divide x by 2, so I'll just subtract 2y from both sides. So I get 600 minus 2y equals x. And that's what's going to go into my equation over here to make it as a function of one variable. Okay. So now area, and that's going to be now as a function of y, will equal instead of writing x, I can write the 600 minus 2y. So there we're using our constraint and then times the y, and that's going to give me my area. And this area now is a function of x, a function of y. One unknown. So we take the derivative, and we get a prime. (600y minus 2y squared). I'm sorry, that's a, excuse me, not a prime, pardon me. Let's get rid of that prime so we don't confuse anybody. So that's area as a function of y, just multiply it out. Now we can take the derivative. a prime of y, and that's just going to be 600 minus 4y. And again, a prime equals 0, no, a prime undefined. I'm sorry, equal to 0. Yes, it could be a 0, but it can't be undefined. No. All right, so we take a look at this. So we just set this equal to 0. So 600 minus 4y equals 0. So if I add 4y to both sides, it ends up 4y equals 600, or subtract 600 divided by negative 1. So y equals, and 4 goes into 600, 350 times. So that's y. Okay, now if I want to find out what x is, and over here, from my constraint equation, 600, x equals 600 minus 2 times y, and y is 150. So x equals 600 minus 300. So, I'm sorry, x equals 600 minus 300, so x equals 300. So those are our dimensions, x and y, so it's going to be 300 by 150 feet. Okay, and you can always check that to make sure these all add up. So if we have y is 150, so I got 150, and 150 is 300, and 300 is 600, and then 300 plus 300 is 600, so that looks all right. We could double check to make sure it actually is a relative minimum, so we can do a first derivative over here. And this is a prime, and that was at 150. And if I put like 100 in here, this is going to be, if I put 100 in here, this is going to be positive. And if like I put 100 in here, and if I put 200 in here, that's going to be negative, 600 minus 800. So it does look like my area is going from positive to negative. So it looks like I do have a relative maximum there. Okay, but what we want is we want the largest area, so now we have to multiply this, so you are going to have to multiply, so hopefully it's not too difficult, but you have to remember long division, so I can say 150 times 300, and that's going to be pretty easy. I can just put a couple zeros there, 0, 0, and then 3 times 0 is 0, and 3 times 15 is 45. So it looks like I've got 45,000, so 45,000, and that's going to be in feet, so that's going to be feet squared. So that's your maximum area. Okay, so that's not too difficult. It's like I said, it's a variation on like the river problem we've done. So take a look at that. It's not too difficult, and it gives you a good concept on how to use the derivative and maximize some of these functions.